First couple of pages in this packet involve us exploring the nature of inverse trig functions and also determining how they kind of tick involving derivatives of calculus of it. So then after that, it'll be structured the same way every other unit is, and that is you get a lot of time to practice. Right? So we're still we're refreshing our memories from pre-calc slash possibly even learning this for the first time, because with inverse trig functions, and often it happens a lot where you start running low on time in pre-calc, algebra 2, and it's like, all right, well, we don't really have time to do the whole unit, so just hit second sign to get your answer. And that'll do the job for you. And you never really have an idea of why you're hitting second sine or second cosine on your calculator. Right? So this is going to kind of go back to basics a little bit, give you a sense of why things work the way they do, and then we'll go on from there. Right? So in the notation, we have the -1 as a power for cosine corresponds to the arc cosine. -1 as a power for sine corresponds to the arc sine. Right? I prefer to say arc sine, arc cosine, and things like that, rather than saying inverse sine, inverse cosine, just because there's less syllables. So the issue there, though, I think, is people like this notation better because it's on their calculator. I actually like this notation better, not having anything to do with the calculator or teacher versus student, making things more complicated than they need to be. I'm not going to screw up any placement of exponents if I write it like this. If I write arc cosine, I'm not going to accidentally put the -1 in the wrong spot, because there's no -1 to put anyway. So that's why I tend to gravitate towards the arc notation. That, and it tells you more about what it is you're looking for. Right? So we'll get into that in a little bit more detail later on, but that's really the reason behind it. Like, we didn't just invent a word for trig to be complicated. Arc cosine is the arc related to cosine, right? An arc length, and that arc length corresponds to an angle, and that is in fact what you're looking for. Right? But before we could even really get started on any of that, we need to go back to what a cosine graph looks like and build off of that. All right? So we know that a cosine graph or a sine graph has a maximum value of 1 and a minimum value of -1. You place it anywhere you want. I'll put it 2 boxes up. All right, we're going to graph this on the interval 0 to 2 pi. Pi was placed for us, so let me just pop a 2 pi down here just for scaling. 2 pi would be about right here. All right, cosine graph always starts off at its maximum. Hits the midline at the quarter-way point. The minimum at the halfway point. Midline at the 3/4-way point. So basically every 2 boxes. And then the maximum back at the end point. Put a nice smooth curve through it. Or at least try to. And that's generally what a cosine graph is. Our calculators will do a better job of it. That's what we're looking at. And it's nothing new. It's done that for years now. It's not an exaggeration. All right. So the question is, all right, now that I know what a cosine graph is, well, what is the arc cosine? It has to be related in some way. It's got the same name, or at least some elements of the same name. All right. But what is it about this graph that translates to the other graph? All right. Well, whenever you're taking an inverse, you're finding a reflection over the line y equals x of some coordinate x comma y. And that corresponds to y comma x. All right. You're taking a reflection over the line y equals x of any coordinate, and all that ends up happening when you do that is that the coordinates get swapped. All right. So if you had 1, 2, it would become 2, 1. All right. So that's the the recipe whenever you're finding an inverse. It's just a question of, will that inverse graph give us something that is also a function? Because we need to work in the world of functions in order for calculus to work the way we want it to work. Right? There are applications of calculus that don't involve functions, but for now we're kind of living in the world revolving around functions. So let me just zoom in here. I'm going to state some coordinates here. I got a nice 0, 1. I can plot that. You do it all in one shot. If you want to state all your coordinates and then reverse them, you could do that, or you could do it one at a time. I think I'll just do it one at a time. I need to establish a scale on my second graph, my inverse graph, because x is becoming y and y is becoming x just by the relationship here. X and y are getting swapped. So what was x is now y. So my pi values will be on the y-axis with my integer values being on the x-axis. All right, I scaled by 2 units in the first graph, so I'll just do the same thing. That'll be my 1 unit away from the y-axis. So I need to plot, instead of 0, 1, 1, 0. All right, going back to my original graph, I had another point here at pi over 2, 0. So I'm going to plot 0, pi over 2. Oh, it's so squeaky. All right, so I'm just switching the values within the coordinates. My third special point along my graph, I mean, there's infinitely many points along the curve, but the clean ones are the ones that we're working with. Pi, -1. This is where -1 would be. So I'm going to plot -1, pi. So again, doing it in the reverse order. All right, I'm running out of graph here. This domain is telling us just to live in the world of -1 to 1. If I connect these 3 points with a smooth curve, I've satisfied that. I have a set of points for a curve that exists on the interval of -1 to 1. So I'm satisfied with what I have here as long as I put the smooth curve through it. All right. Now, the question becomes, well, what if I wasn't given that? What if they just said graph y equals cosine of x? Because if I pop in that function in my calculator, it's going to give me a very specific curve. And in fact, if you've never seen a arc cosine graph before, the first instinct when you see it is like, okay, I typed in something wrong. So second cosine of x, and I'll just do a zoom trig, zoom 7. So it's giving us that sliver of graph, which is essentially what I have here. It didn't seem to want to connect it to the x-axis for some reason, but that's a pixel thing, not a math thing. So the calculator knew to stop there. So how would we know to stop there if -1 to 1 was not given to us? Because I didn't tell the calculator to graph it only between -1 and 1. I just told it to graph it. So it had to know to stop there somehow. And the way it knew is based on the definition of a function. So let's say I went on to the next point, which is at 3 pi over 2, 0. Let me just get a purple pen here. So that one would be 3 pi over 2, 0. All right, if I were to plot that, that would plot right here. 3 pi, so 0, 3 pi over 2. So if I were to extend my curve to catch that point, I'd have a problem. What would that problem be? Why can't I do that? Say again?
It's not a function.
It's not a function because of the vertical line test. Right? It would fail the vertical line test if I included all this stuff here. So I don't want that. So it's telling me that I only want to include values from 0 to pi. All right. So if I go any further than that, if I go any further than that particular interval, then I'm going to have an issue. All right. So this is the only part that I want. Let me do that a little thicker. Oh, actually, I'll use the highlighter. Yeah. All right, so this is the only relevant part of the graph. All right, so, because if you think about it, if you were to graph a sine wave or a cosine wave, it doesn't matter. Just an ordinary sine or cosine wave. I'll put in that a cosine. 7. Generally, I mean, if you want to get a sense of what an inverse graph is, or what it's going to look like, just look at the graph sideways. I mean, technically it's sideways and through the screen the reverse way, which is kind of weird. So I have a sine wave here. I got this parabola there for some reason also. But if I wanted to actually look at have a visual sense of this, what I'd have to do is rotate and then look through the other side. And then I'd have a sense of what the graph looked like. So it would be this perspective. So it's kind of weird to do that with a TV or a piece of paper. So instead, we have to kind of rely on knowledge of trigonometry, the unit circle, and things like that. All right, but you can see here there's a whole lot of graph that would exist if you had to plot, in fact, infinitely many points. If I had to plot all the points in reverse order, you'd have a figure, like a kind of a spiral figure going to positive infinity and negative infinity. Right, so a whole lot of stuff that you don't need. In fact, it's only that tiny segment between 0 and pi that we care about in the original function. Right, so that's a lot to kind of consider. We have a restricted range when it comes to the arc cosine function, and that's where it comes from. Arc cosine only exists between 0 and pi based on everything I was just talking about. Right, our original graph, the only points that I used, the only ones that I ended up using were between 0 and pi. Everything else was excluded. So that's a restriction, right? And it's a weird restriction, but if you take it and reconcile it with some other things that you know, it starts to make a little bit more sense. All right, so let's go back to good old Algebra 2. Remember this bad boy? ASTC?
Yeah.
All right. All students take classes, whatever it is. Oh, calculus. So all the functions are positive in the first quadrant, only the sine function in the second, tangent in the third, and cosine in the fourth. And then their reciprocals go along with it. What this is telling us, 0 to pi, that's the top half. That's this interval here. All right. This is where arc cosine exists. Right, so if you do inverse cosine as an operation on your calculator, you'll never get an answer outside of that interval, if it exists. So let's say I did the arc cosine, I'm in radian mode, I'm sure. Arc cosine of negative, I'll just do negative 1/2. All right, I get this number, 2.094, whatever. Right, 0 to pi, which is 0 to 0. Pi is about 3.14. That number exists on the interval of 0 to pi. All right, that's always going to be the case. The calculator knows those restrictions better than we do, so you don't actually have to worry about the calculator letting you down on this. It's actually the situations where you have to come up with an exact answer, unit circle-based calculations. That's where you're going to have the problem, because in the past, if you needed to find an angle or a ratio from the unit circle, you needed to find every single one related to the particular angle or the ratio. So if I were looking for negative 1/2, cosine can be negative 1/2 in 2 locations in the unit circle. But this is telling me that it's only going to be relevant for one of those locations. So quadrant 3 and quadrant 4 are completely out, right, for arc cosine. Right? The same holds true for arc secant and arc cotangent. If we have time later, I'll explain why that works the way it does. But the structure is similar to sine, where we start off with the original sine function. This time we're doing it from negative pi to pi. So establish my scale here. Sine wave starts off at the midline, increases to the maximum. I'm going to make this 1 and this -1. Increases to the maximum at the quarter wave point, then back to the midline at the halfway point, so we're looking at something like this. All right, if it allowed me to go out to 2 pi, I'd get 1 full cycle to the right of the y-axis, but they don't want me doing that. So I'm going to do the same, I'm going to follow the same trend, but in the opposite direction. And again, you have the luxury of using a calculator here. So if you really, I mean, you look at this and you say, I have no idea what this graph looks like. Again, your calculator does. So sine of x, window, negative pi to pi. Your y min and y max, I know it's supposed to be -1 and 1, but let's say I didn't. It's -4 to 4 right now, so I'll just leave it like that. Hit graph, and you'll get a sense of what it's supposed to look like. And then you can just pick this information right off of your calculator and put it on paper. All right, so it's not the kind of, this is not what you're being tested on. This is to develop the understanding of the calculus that's going to follow. All right, but we're going to run into the same problem here that we did for the cosine, and that is there are some points that are going to be necessary and some points that are going to be superfluous, I guess. All right, so well, let's work inside out here. We have a nice point 0, 0. If I'm reflecting that over to line y equals x, again, switching the x with the y, I'm still going to get 0, 0. All right. If I grab this one here, that's pi over 2, comma 1. I'm reversing that to make it 1, comma pi over 2. So I'll put my 1 here. Let me do that in black, actually. So 1, comma pi over 2 would be right here. All right, so far not breaking any rules. If I connected these 2 points with a smooth curve, it would still pass the vertical line test. All right. I would at least try to grab pi comma 0, but it's not going to be worth it because it's going to go off the grid, number 1. And number 2, that would be a bad point because that would cause the graph to loop back upon itself. If I plot 0, comma pi, it's going to put me on the y-axis. It's going to create a loop that would fail the vertical line test. Right? So I don't want that. So I would ignore anything beyond this point. Also, they're telling us to graph it on -1 to 1. Right? So I would exclude anything beyond 1 anyway. Right? So a couple of good reasons why. Also, it's sort of nifty, but everything it's a world of opposites. Everything in the world of inverses is the exact opposite of the world of ordinary functions. So the domain becomes the range becomes the domain. Horizontal asymptotes become vertical asymptotes. Things like that. Well, that last one's not always true, but there are exceptions because if something is undefined, it doesn't necessarily translate. But there are some things that you can rely on. And one additional thing that you can look for is not the vertical line test, but the horizontal line test in your original function. Because the horizontal line test does to the original function what the vertical line test does to the inverse function. So if there are any points that would fail the horizontal line test for the original function, that would give you a clue as to what would fail the vertical line test for your inverse function. So I'd look at this and say, well, I don't want anything past this red dot here because that would cause me to fail the horizontal line test. Because if it fails the horizontal line test here, it's going to fail the vertical line test there. Right? So that would be my indicator that I would actually want to stop here, or start here and stop there. All right? So the next and last relevant point would be right here, negative pi over 2, comma, negative 1. So negative 1, comma, negative pi over 2. Let me just get my pi over 2 negative here. Something like that. All right. Put a little too much pizzazz at the end of it, but some kind of bowed curve going in. But that's the idea. All right. So what we get from this is that the relevant points in my original graph, again, which would correspond to the relevant points in my inverse graph, only happen on the interval of pi over. I'm like blocking everything out now. Only happen on the interval of negative pi over 2 to pi over 2. All right, so that gives us the range of our arc sine graph. If we're looking at ASTC, that corresponds to these quadrants. All right, negative pi over 2 is just dialing back 90 degrees from 0. And then pi over 2, that's 90 degrees. All right, but we're speaking in the language of radians here. So all that discussion, or all the talking that we did related to degrees versus radians, why radians are important, all that stuff we talked about yesterday, there's a reason for it. The conversation is in the language of radians. Right? And so we got to be careful about that. For the arc tangent, that's actually pretty easy. I can do that quickly on the side with just a rough sketch. So the tangent function has vertical asymptotes. And like I said, a vertical asymptote doesn't always become a horizontal asymptote for an inverse function, but it does very often. This is one case where it does. So the tangent function has vertical asymptotes at negative pi over 2 and pi over 2. And then you have a graph that looks something like this. And then it repeats, just like a sine wave, a cosine wave. It propagates outward. So in the next interval, you have the same graph repeated, same graph repeated, same graph repeated in both directions. All right? So if we rely on the fact, I guess, that in this case, vertical asymptotes become horizontal asymptotes, you'd be looking at a figure that's just a rotated version, rotated and reflected, but it just seems like it's like a side view of your original tangent function, but restricted between negative pi over 2 and pi over 2. Again, because what we're focusing on here is the range of our inverse trig functions. All right, so how high and how low will they go? All right, in this case, it's bounded by your vertical asymptotes for the original function, so those become the natural boundaries of your inverse trig function horizontally, or at least as a horizontal asymptote. Yeah. All right, so that at least justifies why arc tangent has the same range as arc sine and arc cosine. And it's really, I mean, I guess I don't have to do it. The explanations for the other ones are very similar. Arc tangent is almost the same, and the rationale behind, I'm sorry, arc cotangent. The rationale is the asymptotes for the cotangent function are at 0 and pi, rather than negative pi over 2 and pi over 2. All right. So again, I mean, it's hit or miss because this is, in theory, something that should have been explored in pre-calc. And I don't know, I've often been in this situation where it's like, I know it was taught. I don't remember being in the room when that happened, but I'm sure it happened. But this is also one of the lessons that goes out the window first when you have like a ton of snow days, and it's like we just don't have time for it. So maybe it didn't happen. So if this is the first time you're seeing this and it looks weird, it's because it is weird. There's no other way to say it. Now you see something like arc sine of -1/2. Oftentimes that's a calculator question, but it depends on how the question is phrased. It might ask you to put an answer in a particular form. So if I do arc sine of -1/2, and again, we're living in the world of radians here. I can do inverse sine of -0.5 and hit enter and I get that. All right. So again, depending on the instructions, like the ones that follow say to do it using a calculator. So if I get a hideous decimal as an answer for numbers 3, 4, and 5, I'm not surprised. I get a hideous answer for numbers 1 and 2, I don't know what to make of it because I don't really have a sense of whether or not I'm supposed to be using the calculator to begin with. Interpreting what the question is asking is the key to everything. So just take it a step back here for a minute. When you have something like the arc sine of -1/2, that's always equal to some angle, right? Some angle theta. All right. So then one thing you could do, because most people they see the arc sine, they don't like it. One thing you could do is take the sine of both sides. So on the right-hand side, it's just the sine of theta. On the left-hand side, it's the sine of the arc sine of -1/2. All right. Yeah, -1/2. All right, one of those, I mean, maybe you used it twice all year in pre-calc, but you learned it. It's a function of an inverse. You plug a function into its inverse, you get x as an answer. You take the inverse, plug it into the original function, you get x as an answer. X is the thing that's contained within the trig function in this case, specifically a -1/2. Basically, a function will cancel with its inverse to whatever's contained within the inverse itself. Right? So how is this any more beneficial than that? I don't know. It depends. Because what I've noticed in the past is that people will look at the sine of theta equals -1/2 and say, I at least see something familiar about that. That's more comfortable to me. This makes absolutely no sense. I don't even know what I'm supposed to do here. Right? So well, what is that asking us for? Right. It's telling us, well, obviously that the sine of theta is equal to -1/2. But let's think about the unit circle. Where is sine of theta equal to -1/2? Now, I'll rephrase that. What angle has a coordinate where the y value is -1/2? Because again, we talked about I took a whole period yesterday talking about it. The whole point behind knowing the unit circle is so that when you have the coordinates for any angle, those coordinates are cosine of that angle, comma sine of that angle. So if you know the coordinates, you know the trig function. So at 90 degrees, for example, the coordinates are 0, 1. Cosine of 90 degrees, 0. Sine of 90 degrees is equal to 1. But again, we're living in the world of radians, so I wouldn't say 90 degrees, I would say pi over 2 instead. Right? So you either have a completed unit circle in your possession, maybe it's on your phone, maybe it's on paper, but you can actually look at a unit circle right now and tell me 2 locations on that unit circle where the y value is equal to negative 1/2. In radians.
7 pi over 6 and 11 pi over 6.
7 pi over 6 and 11 pi over 6. All right, so we'll start with that. All right, so very important. Both of those are wrong. All right. They'll get you to the right spot on the unit circle, but it's not answering the question in the way that the question needs to be answered, because it's restricted based on the range of the inverse sine function. Inverse sine only exists between negative pi over 2 and pi over 2. All right. So that means, first off, I'm looking for an angle that's only in this, the first or the fourth quadrant. All right, so let me just do a little ASTC here. Get rid of the irrelevant quadrants. Oh, and also, I just typed it into the calculator and I get a negative number. Neither of these numbers are negative. That's an even more obvious reason why we don't have the right answer yet, right? But both of these are necessary to get us to the right answer. All right, so I just crossed off the second and third quadrant because they're not relevant. I only need fourth and first quadrant because the arc sine function only exists between negative pi over 2 and pi over 2. So one of these two are out. Which one? 7 pi over 6. That falls in the third quadrant. All right, so let's get rid of that. Now 11 pi over 6, if you plot that will go into the fourth quadrant, but I need to represent it as a negative coterminal angle. Negative pi over 6. So negative coterminal . All right. So we needed a negative answer that would get us to the same place as the 11 pi over 6. All right. Good thing about the unit circle is that you could use it to your advantage. Right. So I'm not going to pull it up right now. But basically, every step that you take in the counterclockwise direction, you can take the same number of steps in the clockwise direction, just slap a negative sign onto it. So once you identify where 11 pi over 6 is, say, okay, well, I have to make the same movement downward to get to 11 pi over 6 as I would have to make to get to pi over 6. So it's just negative pi over 6. Like, there's no math to do. It's just knowing your unit circle and knowing how to actually operate it. Also, just going back to the calculator, because, I mean, I can preach, I can lecture, I'm pretty good at it, but people still aren't going to listen, or at least I'm not going to get 100% of folks buying in. So what will happen is people, I mentioned it yesterday, I think, people have every intention of doing this unit circle thing, and then just it never happens, and they pay the price. One thing you could do, if you're really in a jam, assume that that is some multiple of pi, divide out the pi, math bracket, if it's math brackable, and slap the pi back on. Right? Because the calculator is giving you a radian answer. So you could get it with the calculator. I mean, it's stuff that you have to memorize. It's more, I mean, you're memorizing something one way or the other. But if you get a funky decimal, and you think it's a clean unit circle type number, divide it by pi, math bracket, and slap a pi on it, and you'll have your answer. Right? So I showed a lot of work for this, but hardly none of it, I don't think any of it had to be shown. Because as long as you know what the question is asking, you can get it. Because it's saying here, what is the angle that has a ratio, a cosine ratio of negative √2 over 2? Right? So cosine is the operative term here. So cosine is the x value in my unit circle. So give me a radian measure where cosine, or the x value of a coordinate, is negative √2 over 2. Well, that would be a positive √2 over 2. I need a negative. But that's you're in the right realm though. It's definitely some kind of pi over 4.
3 pi over 4.
3 pi over 4
5 pi over 4.
and 5 pi over 4. Oh, you did?
Yeah.
Oh, I thought you said pi over 4. My bad. So, again, domain range restrictions. One of these is bad. Which one? 5, because 5 pi over 4 falls in what quadrant? Third quadrant. The inverse cosine function is only in quadrants 1 and 2. All right, so we're only going with the 3 pi over 4. All right, so strictly based on knowledge of the unit circle. Again, you can do it with the calculator in some fashion, but when we talk about this a little bit more tomorrow, you're going to see, especially when we get to numbers 4 and 5, how the calculator could fail you. All right, so numbers 1 and 2 dealt with cases where the unit circle is appropriate in terms of the solution. I also talked about how you might get around the whole unit circle thing, but for numbers 3, 4, and 5, you have to use the calculator when directions say as much. So the idea is to, know how to use the calculator. So arctan is the same as saying the inverse tan of negative 0.3. All right. And again, that inverse tan function is second tangent. All right, so as long as you know that arctan corresponds to inverse tan, you'll know what to hit on your calculator in order to get the result. In this case, you're getting something in the neighborhood of negative 0.29. So I'll just do a little approximate symbol and say negative 0.29 radians. All right. Now, you may look at this and say, okay, well, then forget the unit circle. This sounds great. I'll just do this every time. All right. Well, again, depending on the directions, you might have a problem with that. Also, you get to something like number 4, where it asks for an arc cosecant, and there is no arc cosecant button on your calculator. So the best you could do is type in 1 divided by the arc sine of the negative 2.4, but then something terrible happens. Error domain. Now, we know at this point that means one of two things. Either we screwed something up, or the calculator's not going to be able to do it for us. All right, so what we have to do, or at least in this one instance, is just kind of play around with it algebraically, or at least pencil, paper, not calculator, see what the story is, and then maybe we'll have a technique that we can use moving forward. All right, so again, the result of an inverse trig function is always an angle, not g, an angle. I don't know why I did that. If I took the cosecant of both sides to get rid of that inverse, I would have cosecant of theta is equal to negative 2.4. All right, so take the cosecant of both sides, left-hand side becomes negative 2.4, right-hand side becomes just cosecant of theta. I just prefer to write it this way. All right. Doesn't look like our situation is improved, but we do actually know things like SOHCAHTOA and everything that goes along with it, all the other ratios. And one of those ratios would be the cosecant ratio. Cosecant of theta in general is the reciprocal of sine, so it would be the hypotenuse over the opposite. Okay, so if they're telling me that I have a cosecant ratio equal to negative 2.4, I could write it as negative 2.4 over 1, just to make it a fraction. And what that would give me is the corresponding sine ratio, because then sine of theta would have to be 1 over negative 2.4. You put the negative wherever you want. I'll take the reciprocal of the cosecant function as long as I take the reciprocal of the other side of the equation. All right. Then I could solve for theta by taking the arc sine of both sides. All right, so then theta would be equal to the arc sine. I'll write it as arc sine. I'm going back and forth on purpose just so you get used to it. Inverse sine, sine with that -1 power, and arc sine, I mean the exact same thing. All right, so I'm going to write it as arc sine of 1 over -2.4. All right, and this is going to lead us to a shortcut. Again, the notation, you have a choice of going inverse sine notation with the power of -1 or writing arc sine, but I've seen it before, it's even happened to me. You see that power of -1, it's written on paper in front of your face, you acknowledge that it says -1, but for some reason you treat it as though it says prime. Like, you'll see signs of -1, and all your brain will interpret it as, because we've been doing this all along, is the prime, as in derivative, not inverse. And that's just dangerous. So, recommendation, go with arc sine. You don't have to worry about notation as much. All right, but what does this tell us? I have a recipe, I put it right in the calculator. Inverse sine of 1 over -2.4. Get a result, get an answer. But we also get a rule out of it. So approximately equal to -0.43 radians. All right, so just do a little comparison here. We originally had cosecant as an inverse of -2.4. That ended up being the same thing as the inverse sine of 1 over -2.4. All right, those are exactly the same. But think about what happened. We took the reciprocal. And we took the reciprocal here. So you could work with the reciprocal of the inverse trig function. That sounds like a lot, but instead of arc cosecant, you take arc sine, as long as you take the reciprocal of the thing on the inside too. All right. If you do that, then it's calculator friendly and you're ready to go. You won't get the error message. At least you won't get an error message when you shouldn't. You know, sometimes the answer is just undefined. If that's the case, you should be getting an error message, but that's not the case here. So that allows us to look at number 5 and say, okay, well, instead of doing all that, how about I just do the inverse tangent of 1/3? And again, error message or no error message, there still isn't a arc cotangent button in your calculator. So you need something else, one way or the other. And this would be your something else, 0.32, yeah, just 0.32 is fine. The moral of the story here is really the idea that it's all coming back to the unit circle, true. You're going to need to know how to do all this stuff when you're doing the calculus, also true. But it's not the driving force necessarily of all the calculus stuff that'll follow. You'll see in a minute, we're going to switch gears a little bit. This is going to work its way into the problem-solving parts of the calculus. So we'll take a derivative. We'll have some particular x value that we have to plug in. You'll get to a moment like this where you have to do something with an arc cosecant of -2.4. And if you don't know these skills, you won't know what to do. And you know how I've been saying all along, don't forget you have a calculator. Before every test, don't forget you have a calculator. Some of us forget. By the time you remember, like we'll be on the next and I think last unit test of the course, by the time we get there, you'll be like, all right, I'm not going to forget about my calculator this time. And then you'll get to like 4 questions that involve this concept. And, okay, cool, I remember that I have a calculator. But it's not doing anything for me because I don't know what to type into my calculator. All right, so the pre-calc stuff is the important stuff in this topic. You'll see the calculus stuff is not, I mean, okay, you'll look on this page and you'll say, okay, yeah, the calculus stuff is easy, huh? Yeah, no, it looks terrible. It's actually not as bad as it seems. But we're looking at still a little bit more pre-calc stuff. We'll start with something completely numerical, something that you could actually type right into your calculator. I could do this right now. Sine of the arc cosine of 4/5. 0.6, you want to do math practice, clean it up, sure, 3/5. Great. So you could do that, but let's come up with a more general approach, not in the classic teacher sense of we have an easy way of doing it, so let's figure out a way to make it more difficult so I can kill a class period. Not like that, more so that we could apply it in variable situations. You look at 7 and 8, immediately off the bat, it's non-numerical. All right, so this is some angle theta. Theta is equal to the arc cosine of 4/5. All right, which based on everything that we were talking about on the previous page corresponds to the cosine of theta being equal to 4/5. All right, so again, algebraically it's a slight manipulation, but it makes a big difference because we know cosine ratio. We know that that's adjacent over hypotenuse. So I could draw a triangle, a reference triangle with a reference angle theta. I can place my adjacent side, make it a 4, my hypotenuse, make it a 5. What's my missing side? 3. Nice Pythagorean triple. All right. What this represents is a visual representation of the arc cosine of 4/5. All right, this triangle is the arc cosine of 4/5. Basically telling us that if I could figure out the missing angles in this triangle, I would then know what the arc cosine of 4/5 is. The good news is I don't need the arc cosine of 4/5. I need the sine of the arc cosine of 4/5. Since the arc cosine of 4/5 has been defined as theta, I'm really just looking for the sine of theta in that triangle. The sine ratio, opposite over hypotenuse. The opposite side, 3, the hypotenuse 5, 3/5. All right. I mean, it was way quicker on the calculator, but again, it didn't have any variables in it, so the calculator doesn't have a problem with it. It would have a problem with 7 or 8. But we could use a similar strategy for number 7 to come up with a ratio that represents the sine of the arc cosine of x. All right. So, bless you. This is theta. The result of an inverse trig function is always an angle. Just repeat that to yourself like 10 times, and you should be fine. All right. The result of an inverse trig function is an angle. And then, 9 more times after that. I'm not gonna do it. I already memorized it, so I'm good. All right. So I could rewrite it as a cosine of theta is equal to x. Same structure as the last problem. Right, well, the x isn't a fraction. All right. Well, now it is. It's fine. Adjacent hypotenuse. Triangle. Basically the same triangle. Adjacent side is the unknown. The hypotenuse is equal to 1. I'm going to need the sine ratio, which is the opposite over the hypotenuse. Right? So I'm going to need to do basically what I did here, which is going to require me to figure out the missing side. Not a Pythagorean triple anymore, but not impossible to figure out. Square root of what?
1 squared minus x squared.
1 squared minus x squared, which I'm going to simplify to just a 1 minus x squared. Good. All right, And so again, since we're looking for the sine of theta, which would be the ratio of the opposite side to the hypotenuse, we pretty much have it. So I'll just write my answer above. The opposite side is the square root of 1 minus x squared. And the hypotenuse is equal to 1. I'll write it over a 1 just to have it, but you obviously, if you're simplifying, you wouldn't write that. All right. This is a very powerful relationship here. It just doesn't seem like it would be. But what it does is it allows us to take something that's trigonometric and turn it into something that's algebraic. If I ask you right now to take the derivative of the sine of the arc cosine of x, you wouldn't be able to do it. Because it would be chain rule, and that's all well and good, but the inner function is the arc cosine of x. You don't know how to take the derivative of that yet. But if I tell you that these two expressions are equivalent, then you can just take the derivative of this, and it would be the same as the derivative of that. So by knowing how to convert over to an algebraic form, half the battle's already won. And also, I mean, we don't really get to too much involving antiderivatives in this course, but that's actually the part that makes calculus hard. You know, once you've mastered everything about derivatives, you know, you take a calculus class where they turn around and have you do everything in reverse. So find the expression that has a derivative that's equal to this expression. What they're most commonly going to do, if they're going to try to stump you, is give you an expression in this form, and you have to recognize that that is equivalent to taking the sine of the arc cosine or the tangent of the arc secant, whatever, and then work off of that, right? Because generally, I mean, once I show you the rules, you know, it becomes a debate where it's like, well, finding derivatives involving trig is not that difficult. Algebraically, they can be a nightmare. So sometimes substituting out an algebraic expression for a trig one is the way to go. But that's baby steps towards that. Eventually you'll get there and you'll remember this, hopefully. But until then, we're taking a lot of things on faith, I guess. All right, so, and again, we want to streamline it a little bit. Secant of the arctangent of 3x. Again, the result of an inverse trig function is always an angle. So this whole thing here amounts to some angle theta. All right? So I could write arctangent of 3x is equal to theta, just to then take the tangent of both sides. But it's all going to amount to the idea that the tangent of theta is equal to 3x. Again, trig ratios. So I'm going to write it as 3x over 1. I have my opposite side, and I have my adjacent side. That's the TOA part of SOHCAHTOA. All right. So I'll pop in my opposite side, my adjacent side. We'll just have to figure out what the missing side is. Pythagorean theorem. Again, not as easy as 3/5, but doable. And then once we have that, we're going to find the secant of our theta, which by SOHCAHTOA is hypotenuse over the adjacent. Always a good idea to kind of have in mind what you need, because if I got to this step, let's say on the outside it was like cotangent, like the cotangent of the arctangent of 3x. The ratio for cotangent is adjacent over opposite. So when I go to look for that, I don't need the hypotenuse, so I wouldn't waste my time solving for the missing hypotenuse. Right? But what would that hypotenuse be?
Radical 1 plus
Exactly. And again, all Pythagorean theorem. All right, so I take my hypotenuse, divide it by my adjacent, and that gives me my equivalent expression, which would be that radical over 1, but again, you don't have to write the over 1 if you don't want to, but I'll do it. All right, so another algebraic expression that's equivalent to the given trigonometric expression. When you start getting into secants and cosecants when taking the derivative, algebraic expressions, a substitution might make more sense because the derivative of secant of just x is secant x tangent x. So if I were taking the derivative of this, it would be secant of the arctangent of 3x times tangent of the arctangent of 3x, that part will actually be nice, times the derivative of the arctangent of 3x. Again, we don't know that, but it would be a disastrous mess. But once you simplify that down, you get the exact same answer that you would get if you took the derivative of this with chain rule, log differentiation, whatever method you like. Right? So the benefit, I don't know. I'll say it's obvious, but there's always some disbelievers, I guess. So let's actually learn how we can come up with some rules related to inverse trig derivatives. So again, the result of an inverse trig function is always an angle. So let's call this some angle theta. All right. So I could write, I'll actually write it out more carefully this time. I won't skip any steps. Theta equals the arc sine of u. I'm purposely leaving a little space in front of the arc sine. All right, because again, the result of an inverse trig function is always an angle. The expression that's contained within, that's always a ratio. All right, so there's a little hint as to how you could skip some steps, but I'm not going to bother with that right now. I'm going to take the sine of both sides and get, well, this side's going to become a u, so I'm going to write it as u equals the sine of theta. All right, it becomes notation intensive here because you got to sort of have an idea of what it is you're looking for in a final answer. But in order to do that, you need to know what the notation is telling you. So I'm saying again that the result of an inverse trig function is always an angle, right? I've said that, I got to be close to 10, maybe 7 or 8 at this point. But just focusing on the idea that I can replace this with theta, it tells me that what I am ultimately looking for is d theta dx. All right, that's my goal. So I have a u and a theta. So I'm already behind the 8 ball here. Right? I need to somehow introduce x's here. And also, by the way, I need to get rid of u's because this just says d theta dx. Right? So what we can do, at least as a first step, is take the derivative, just as you see it. I'm going to find du d theta. All right, so if this were 2 units ago, I would give you the problem as y equals the sine of x and say find the derivative. You would say the derivative of sine of x is cosine x. All right, here I'm just replacing the u. This isn't even implicit differentiation. I'm replacing the y with a u. I'm replacing the x with a theta. So my derivative is going to be pretty much the same, except it's going to have a theta instead of an x. All right, the rest of this process is actually just going to boil down to the idea that I need to somehow make that du d theta into a d theta dx, which is kind of a weird thing to think about, but it's actually very doable. So what I might consider doing, well, I'm looking at my expression here compared to what I want. the d theta is on the bottom. I want it on the top. All right, so I'll do that. I can't just do it to one side without doing it to the other. So I'll do that. So that's something. I need some x's, and I need to get rid of that du. All right, so, but let's focus on the trigonometric part of it here. If I can get rid of that, it's going to go a long way. All right, so let's take a look at this expression here. The u equals sine of theta.
Why would you want to get rid of that and not the d theta or the du?
Well, we're going to get rid of them both.
But you have to get rid of cosine theta?
Yeah, well, I'm going to show you how to get rid of both. I'm just starting with this. All right, so sine of theta is u. So we could write it as a sine of theta equals u over 1. I'm going to draw a triangle. All right, so the skills from the problems that are right above this, the 3 examples, are going to come back into play right here. The sine ratio is opposite over hypotenuse. All right, so opposite would be u, hypotenuse would be 1. What I need is the cosine ratio. Now, you may even look at this and say, well, 1 over cosine, I could change that into secant, but I'm not going to do that right now. What would the missing side of my triangle be? The square root of something. 1 minus u squared? Yep. All right, so 1 over cosine. I can change that now because, yeah, so 1 over, adjacent over hypotenuse for cosine, which would be the same. 1 over h would correspond to h over a. All right. So before, when I was saying I could take my 1 over cosine theta and make it into secant, I could do that, but it's all going to come out in the wash anyway, because the ratio h over a is the ratio for secant anyway. All right, so you can grab it either which way. So my hypotenuse, which is 1, would be over my adjacent, the root of 1 minus u squared. All right, so almost there. The grand finale coming up. We have a d theta du. I'm going to leave a little space, then an equal sign. 1 over the root of 1 minus u squared. All right. Again, don't lose sight of the goal. I got rid of my cosine of theta. That's great. I have an algebraic expression that takes its place, but it's in terms of u, so that's a little annoying, but I can deal with it. The big issue is I need a d theta dx instead of a d theta du. All right?
Why do you want the d theta dx?
Because that's what they're asking this for. It's d dx of this theta.
Okay.
So that denominator there is telling me what I need to have my final answer in terms of.
So, okay. Yeah.
All right, so we can multiply that ratio by a new ratio that's going to keep the d theta the way it is, but get rid of the du. What would that ratio be? du dx. Good. But you can't just multiply to one side without the other. All right, so that's a little chain rule aspect to it, because any time we had a chain rule situation, we're always multiplying by du dx. But if you multiply by du dx, the du's would cancel, and you would be left with d theta dx. And so this ends up being your derivative rule for the arc sine of any function u. All right, so I can give you anything at this point, and you won't have a problem with it because now you have a model that you can use. And you don't have to go through this entire progression to come up with a solution. So if I said something like d dx of the arc sine of 5x squared, this would be my u. follow the model. 1 over the square root of 1 minus my u, which is 5x squared, multiplied by the derivative of the u. That's the only thing that'll make it complicated. If you have trouble finding the derivative of whatever the u is, then you're going to be in for a ride. But otherwise, it's pretty easy. What is the derivative of 5x squared? All right. So the derivative of this arcsine function is that. And it hardly took any effort beyond knowing a rule. All right. Let's do the tangent one now. The cosine, the co-functions, so cosine as it relates to sine, cotangent as it relates to tangent, they're just negations. You can go through the work. I'll give you time to do this on Monday. But when you go through all the work, the arc cosine derivative is just going to be the negative counterpart of this. Not a reciprocal, just a negative. So take that positive one and make it a negative one, and you have the rule for the arc cosine. All right, so practicing this on your own is valuable. It's just you don't actually need to do it to derive the rule.
Like for a test, would we just have to know the rules, or would we have one of those?
You'll have exactly one of these situations where you have to do it on. All right, so again, the result of an inverse trig function is some angle theta. So we can say that theta is equal to the arctan of u, which corresponds to the tangent of theta being equal to u. All right, you can flip it around, or you could just not write the tangent of theta equals u and go directly to u equals tangent of theta. When all is said and done, you're going to need them both anyway, so it doesn't make a difference. But we would then take the derivative of u with respect to theta, du d theta. What's the derivative of tangent of theta? Secant squared theta. Start to see why we spend so much time practicing derivative rules. Like when I say derivative of tangent and you immediately come back with secant squared, that was the whole point. So that you're sitting in Calc 1, Calc 2 in college, and the teacher says derivative of secant, and you come back with secant tangent, and the rest of the class is still kind of looking around, being like, where did this black magic come from? Like you'll already have it. All right. So I'm going to do a reciprocal here to get me a d theta du. And I'm going to do a reciprocal here. Now, if you want, do it the opposite of the way I did before, which is to say, okay, well, I know the reciprocal of secant squared is cosine squared. Or you could just write 1 over secant squared. All right, and the rest of it is just cleaning it up. So tangent of theta is u over 1. Opposite side, adjacent side of the corresponding right triangle. The opposite is u. The adjacent is 1. We're just going to need the hypotenuse. One plus u squared under that radical. All right, now the secant function has a ratio of hypotenuse over adjacent, but we're going to be squaring that. So 1 over, I'll take my hypotenuse, put it over the adjacent, and square. And surprisingly, it cleans up because it didn't look like it was going to. D theta du, leave a little space, would be equal to 1 over 1 plus u squared. All right, and that's again because if I square this radical, it's gonna go away, leaving me just a 1 plus u squared. Square of 1 is a 1, a fraction over 1 is itself. So this 1, this numerator stays as a 1. That whole quantity squared on the bottom just cleans up to a 1 plus u squared, which is really nice. So then all I have to do to get my d theta dx, which is my ultimate goal here, is multiply both sides by du dx. The du's would cancel on the left, leaving you with what you want, d theta dx, and on the right, you now have a rule. All right. So we have a rule for sine, we have a rule for tangent, and on Monday we'll have a rule for secant. And then once you have those 3 important trig ratios, the 3 most important trig ratios, then you'll know all their cofunctions. Because all you have to do is slap a negative onto this one, and you have the derivative of the arc cotangent. All right? But again, I mean, it's a journey, so I'll do another one with you on Monday, and then you'll practice the remaining 3 on your own, and then we'll see where we're at. And then we'll mix more of that pre-calc stuff back in. Unit circle, all that good stuff. Yeah. It's a short unit though. I think in the first 5 minutes of class on Monday I will have taught you the last thing, the last bit of direct construction. The rest is practice. We're looking at 14th or so. Okay. 14th, 15th.